Lesson 1.6 is going to be looking at some different area formulas for review with the purpose of linking it to velocity graphs and finding total distance and displacement. Before we look at the graphs, just a couple of refreshers. The first thing is some area formulas here. These are just basic things that hopefully you remember from geometry. The first three are going to be the ones that are the most valuable to us for our calculus work. That is the area of a rectangle, which is just the length times the width, or you might think of it as the base times the height. Basically the measure of the two different sides that form a right angle somewhere on the rectangle. A triangle has the exact same formula. Again, that's why you can think of length and width and base and height as sort of the same thing, but you do need to cut the answer in half. Though we'll be able to get through this lesson just by using rectangles and triangles, it is optional to also use the area of a trapezoid in order to find some of the areas for this lesson. You can find the area of a trapezoid by adding up the measure of the two bases, dividing that answer in half, and then multiplying by the trapezoid's height. If this is too complicated, though, don't worry about it. Also, here's the area of a circle, just in case you forgot. Another important thing to do before we start this lesson is to revisit a problem at the end of our previous lesson that had these two graphs of the exact same walk that somebody took, where they covered 63 meters in 7 seconds, maybe more of an extremely fast run, not a walk. Even though both graphs had all three of the same pieces of information, which is 7 seconds, a total distance of 63 meters, and a velocity of 9 meters per second, the graphs look completely different. How could this be? The conclusion we were able to reach is that we were looking at a distance graph and a velocity graph, where on the distance graph, the ending value 7 and 63 give you the total time and the total distance traveled, where the velocity is represented through the slope. On the velocity graph, though, the ending x value and y value give you the velocity in total time instead of the total distance in total time. Instead, if you multiply the two numbers of that coordinate 9 and 7 together, you get 63, which is the total distance. This gives us this very important conclusion that we can find total distance and displacement by taking the area under a graph of a velocity function. So here we have a couple of example problems. Find the displacement and the total distance traveled for the following velocity graph. So these are probably some type of like v of t style piecewise function. We don't necessarily need to be able to create whatever the function is, but that's what we're looking at here. In order to get total distance and displacement with a velocity graph as opposed to a distance graph, instead of looking at the change in y for each of the lines, we are going to create shapes between the graph and the x-axis. This is what the definition of the area under a graph technically means, is the area between the graph and the x-axis. This is important to note because any line that is below the x-axis actually has its area technically above the graph, as it is going to move up to the x-axis to complete its shapes. For our first graph over here, we can get all of our areas accounted for by turning everything into different rectangles here. The rectangles that we have measure 4 by 3, 6 by 1, -3 by 4 because we are moving down below the x-axis here, and -1 by 4. This means that our four areas are 12, 6, -12, and -4. If we combine all these numbers as is, we get an ending value of 2 units. Because we did not take any absolute values, though, this would be the displacement of the graph. If we were to take the absolute value of all of the different areas instead, we would end up getting a total distance value of a whopping 34 units because our -12 is turned positive, so we have a lot of big numbers here. With our second example, we don't have any negative velocities or any graphs that go below the x-axis, meaning our displacement and total distance are going to be the exact same answer. In contrast to the other problem, though, we actually have some sloped lines here on a velocity graph. This would technically mean that our distance graph is something pretty complicated, like some curved line graph, but we're not really concerned with that yet. For now, we're just going to look at how we could get a total distance out of this by breaking this into a series of both rectangles and triangles. So to make things a little bit easier, I went ahead and grayed out all of the area that was under the graph to begin with, and then I made my lines to cut the area into different shapes. So this is what I guess I would have done, but keep in mind that there's more than one way that you could probably split this apart and add up the areas. It's kind of up to you how that's done, but let's look at the numbers based on what I got. Another 4x3 for the first rectangle, a 3x2 for this triangle here, but we have to cut it in half because it's a triangle. Same deal with this triangle, it will be 4x2 divided by 2. And our last two rectangles have an area of 7x1 and 2x1. In total then, this gives us the areas 12, 3, 7, 4, and 2. And since none of these are below the x-axis, they will all be positive, meaning both the displacement and the total distance should be equal to 28 units. The Desmos file for this assignment actually just has all the different area formulas that are at the top of the assignment, as well as what we looked at in the terms and definitions section set up here. So if you want to calculate stuff this way instead of doing it by hand, you are welcome to. Otherwise, we'll be spending a little while thinking about this idea of area being related to total distance with velocity graphs. Thanks so much. See you soon.